All right, welcome to the deep dive. Today we're jumping into deep learning, or DL, which is, the engine behind pretty much every major AI breakthrough we see.
From your phone's camera to the huge language models.
Exactly. So our mission today is to get past the buzzwords and really figure out why this specific type of AI became so incredibly powerful.
And it's interesting because at its core, deep learning is really defined by its architecture. It's just multiple layers of computation, kind of inspired by the brain.
Inspired by the brain, right?
But the real game changer isn't the structure, it's what it can do. It can take in huge, messy piles of unstructured data images, text, sound, and just figure out the patterns for itself.
So it's this idea of depth then. How does just adding more and more layers actually change what the model can learn?
It enables something called hierarchical feature learning. You can think of it like a pyramid. The first few layers learn really basic stuff.
Like edges and colors in a picture.
Exactly. Simple edges, textures, that sort of thing. But then the deeper layers start combining those little pieces into much more complex concepts. Like it'll put edges together to see the curve of a wheel or the shape of an eye.
I see. So it builds understanding.
It builds understanding layer by layer. And the data on this is just undeniable. We saw a 152-layer network outperform an 18-layer one on the ImageNet challenge by almost 10 percentage points?
That's a huge difference. But if the core math, this thing called backpropagation, was figured out way back in the 1970s, were we just waiting around for better computers? Did we miss the boat for 30 years?
That's the million-dollar question, isn't it? And the failure wasn't really algorithmic. I mean, the math was solid. It was a resource bottleneck.
A resource bottleneck.
Yeah, they had this beautiful mathematical engine, but they had absolutely none of the fuel. They didn't have the massive data sets or the raw compute power. It was like having a Ferrari engine, but only bicycle fuel to run it on.
Okay, so the fuel had to arrive, and that was the ImageNet project, right?
That was the catalyst. Between 2009 and 2012, Fei-Fei Li's team saw this exact problem, this data deficit, and they built ImageNet. We're talking 12 million labeled images.
A massive undertaking.
And that set the stage for what we call the AlexNet moment in 2012. They used GPUs, graphics cards, to just power through that data. And it didn't just improve the result, it slashed the error rate. It proved that scaling up data and compute wasn't just helpful, it was everything.
So they had the fuel and the engine. What was next?
Well, even with the power, the process was still a bit inefficient. It needed a better lubricant, you could say. And that innovation was the rectified linear unit, or ReLU.
ReLU.
Sounds technical. But the idea is simple. It's just a more efficient on-off switch for the artificial neurons. It stopped the deep networks from seizing up during training, which is what made training a 152-layer network even possible.
Okay, that makes sense for images. But what about something messy, like a conversation or just a long piece of text? I've heard about this vanishing gradient problem.
Right. With sequential data, older networks, they had terrible short-term memory. A signal from the beginning of a paragraph would just fade away or vanish by the end.
So it would forget the context.
Completely. And that's what led to things like LSTMs and GRUs. They have these spiralized little mechanisms, like a forget gate, that let the network very deliberately decide what old information is important to keep. That finally cracked the long-term memory problem.
And that whole line of thinking led us to where we are now with the transformer architecture from 2017. What was the big leap there?
It completely threw out sequential processing.
Yeah.
Instead of reading word by word, the transformer uses something called the self-attention mechanism to look at every word at the same time. It's massively parallel.
And self-attention is the core of every big language model today. So what is it in simple terms?
The best analogy is that for every single word, it runs a quick search across the entire sentence to see how relevant every other word is. It uses these things called query, key, and value vectors to weigh connections.
So it creates a global context.
An enforced global context instantly. It knows how the first word relates to the last word, all at once. That's its superpower.
So if you put it all together, deep learning's success wasn't one thing.
No, it's a perfect storm. It's a symbiotic relationship between, the mathematical insights from decades ago, the explosion of big data, and the sheer power of modern hardware like GPUs.
So here's the final thought to leave you with. While these DL models give us incredible performance in everything from medicine to self-driving cars, their complexity often turns them into complete black boxes. We know they work, but we don't always know why.
That's the trade-off.
And that's the critical challenge facing everyone in this field. We're constantly choosing performance over interpretability and figuring out how to balance those two things. Well, that's the next great deep dive.